Hello and welcome to Chapter 10, Mobile Security Software with Cloud Management in ISOL 536 Security Architecture and Design. My name is Dr. Alan Dennis. I'm your instructor. Jumping into Chapter 10, it centers on mobile security software with cloud management. We'll talk about basic mobile security architecture. We'll talk about mobile often implies the client cloud design. We'll talk a bit about introduction to cloud. Authentication is not a panacea and the entire message stack is important. Then we'll talk a bit about just good enough security, and we'll close with additional security requirements for mobile and cloud architectures. Jumping into the first section, in order to examine yet another architectural pattern, this example, mobile security products will make use of a cloud-based management software and a software as a service reputation service. Starting into section 10.1, basic mobile security architecture. Figure 10.1 presents the architecture of a hypothetical mobile security protection system. Many of the components are the same as the endpoints security architecture. Incoming and outbound communications have to be established and maintained. And an engine must process system events and examine possible malicious data. So here's your basic architecture. This is the application. This is the system. You've got some sort of intercept that basically is receiving stuff and responding back with events. You've got an engine that executes with a UI that talks to it, and a communication system that's used to communicate outside of this environment, and then something that opens up files. A reputation service is so called because many behavioral data ports are kept about a particular URL, file, or internet protocol. The data is collected from various sources about the observed behavior of the object for which reputation is being calculated. A URL or other object will fall somewhere in a continuum from absolute malicious to reputable good sort of distinction, with various degrees of gray in between those two poles. Based on the reputation service, software can prevent access, present the problem for user decision, or passively allow the access. That's why sometimes you'll see an error message from your computer that says, I'm unable to reach some service right now. What do you want to do? Because it was unable to determine if the thing you were about to interact with, made an executable perhaps, is good or not. It has a reputation of being good. Although it may be apparent when looking at mobile devices, it may not be apparent when looking at mobile devices, they do have permanent storage. It's not necessarily a disk drive per se, but there is storage that is persistent. Files are kept on the device's permanent storage. Applications create files. Applications manipulate files. Device users view and edit files. Indeed, on the device's storage, a typical operating system directory structure does, in fact, exist. There is a tree of directories, folders that is exactly what you would find on your computer or laptop, regardless of which of the usual operating systems you use. On many mobile operating systems, the file and directory details are hidden from the user. Most of the operating system assumes that there is a single user who has access to the files. Since mobile operating systems highlight application functionality, the details of file access are hidden behind application user interfaces. For example, when you take a picture with your phone's camera, that picture persists. That's why you can look at it in something like a gallery. So clearly that is an example of a file that is being stored on a permanent or reasonably permanent storage. So it's a key thing to understand is that while it may not be terribly obvious that it is there, it's not all that different than your laptop. And in fact, Android's not all that different than some of the Linux operating systems. Continuing the discussion of around mobile devices. In 10.2, we learned that mobile often implies a client-to-cloud kind of connectivity. So continuing the discussion, in at least a couple of mobile platforms, no application may install software into the kernel. As was noted in Chapter 3, the system area exists between the application mode and the kernel. There are three layers, application, system, and kernel, which are depicted in figures 10.1 and 10.2. The kernel is not diagrammed as it is not relevant to this architecture. For our purposes, the security issues are approximately the same regardless of whether intercept exists as a part of the operating system, whether it was written and installed within the application. If the intercept service is native, that is part of the operating system, obviously its secure coding and assurance is not under the control of the mobile software maker. Still, the design issues are analogous. So let's talk a little bit about clouds. Communication from each endpoint must flow across the untrusted internet. Any number of networks and internet providers may be crossed as packets are routed. Hence, in figure 10.2, the arrow from the communicator reaches into the internet, whereas disconnected arrows move to the cloud-based services. The distinction between arrows is to indicate the unknown nature of routing and the unknown networks across which the traffic must pass. Usually the commercial services are cloud grade. That is, services are available across the globe so that user access times is reduced. The services are always available with failover systems that can pick up upon an instance failure. Cloud services are usually redundant and backed up to various points of presence, spread out geographically so that a local catastrophic event cannot bring down the service. We will take a look at the backend architecture of a cloud services in the next analysis. One of the big challenges with cloud-based reputation checks is performance. Users don't typically want to wait a few seconds while the reputation of a potential URL is checked. Most of us have come to expect that websites are at the immediate tips of our fingers, and that access and loading of the content should take place rapidly and without delay. This presents a tricky security problem. In section 10.6.1, we learned that the authentication is not the end-all to be-all that will solve all problems. Should the application be the entity that authenticates, or should it be the device? Again, there are arguments back and forth about this design choice, which we won't go into in this example. There are strong reasons for authenticating the device, and that's the pattern that this system employs. If it's the device that's under management, even if the software breaks down, the management service has some concept of the device itself. If the device is lost, it can contain an identifier, regardless of whether the software on it has been reset by a thief. The mobile carrier interacts with the device, and the management service, which is able to identify the device, may interact with the carrier about the device if necessary. Both the management service and the reputation service authenticate the device, not the user. I reiterate that in general, a mobile operating system and architecture assumes a single user per device. Should the communicator authenticate the service, TLS is being used for the device to the server. TLS always validates the server certificate before proceeding. However, the authentication typically only validates the certificate was issued by a known certificate authority and that the certificate is valid for the IP address of the server. In other words, any TLS server that has a valid certificate will successfully pass the server-side TLS valid authentication. What if our mobile security software gets directed through DNS spoofing or to a malicious site? And what if that site presents a valid certificate? So there's a bit of a disconnect here between some of the things that existed when this text was probably written and things that may exist today. The reality is we usually rely on both forms of authentication. For example, on my cell phone, it has facial recognition and locks itself on a regular basis. I can also type in a PIN, but it does have biometrics so that it makes it easy to unlock. That being said, whenever I go into specific types of work-related applications, those are oftentimes secured using another secondary form of authentication, which may be something that is unique to that application. Beyond just the application, such as like email, has a username and password that authenticates in order to actually access something like Outlook on my device. Again, it has to rely on either a PIN that I provide, or it can also leverage the biometric subsystem of my phone. So the point of all that is that we don't just blindly trust the operating system of a cellular phone to assume that the application is also secure. We typically do both. So 10.4 introduces the concept of just good enough security. Depending upon adversaries against whom you're protecting the device, good enough might well be a reliance upon the message's digital signature alone. Alternatively, for high security situations that require more assurance, the addition of a validation of the TLS certificate could be added. In addition to validation of the certificate, authorities signing claim also validate their certificate that is presented by the server, making it difficult to impersonate the reputation server. There is no right answer here. It depends upon the security needs of the organization and how much risk can be tolerated. The point of all this is that you should do enough security that is sufficient for the situation you're in, but and no more. That's true of building software, of securing software, and everything else. It should be a conscious decision of how much of that is being done, but you don't over-engineer it, as we say, or do more than is necessary. We do what is good enough, and when we reach that concept of sashimi, we move on. Just good enough security continued. So in figure 10.3, we talk about a cloud-hosted mobile device management system using the hardware security module. So how do you protect the secret like a private key? In addition to the hardware security module, you can use the hardware security module can help protect that private key that will sign each device certificate and all the messages from the management function to the device as specified above. But HSM are not a panacea, just like the use of TLS is not a security cure-all. Deploying an HMS requires some forethought and architecture. And oftentimes you want to rely on something that's built into the device itself, if at all possible. Continuing the concept of just good enough, here is the order of processing. The user enrolls the security application. The user enrolls a particular device. The device identifier is generated, and it must be sufficient entropy to be unpredictable. A certificate request is generated from the device identifier on behalf of the device. The certificate request is sent to the HSM. A signed certificate is returned. The public key of the signing key pair will be included in the certificate, and a device certificate for the particular device identifier is returned for installation on the device. The device can use public key to verify the certificate signature, and then after enrollment, communications from the device may not proceed before the signature over the device certificate has been verified. This can be done by comparison against a duplicate of the public key, which is kept within the directory copy maintained within the authentication system's restricted subnet. No communication to the HSM is required in order to validate the certificate. The duplicate public key does not require additional extraordinary protections. In section 10.5, we talk about additional security requirements for a mobile and cloud security, or mobile and cloud architecture. The following comprise additional requirements that must be added to those for an endpoint anti-malware application. The use of TLS between mobile device and cloud service. Server-side TLS authentication is required. Each enrolled device will be issued a device identifier. Device identifiers must be unpredictable. Generate and install certificate on each mobile device under management. The certificates must be unique to a device, to each device. Certificate signature must be validated before cloud services may be accessed. The private key to sign the device certificate must not be deployed to any device. A single private key may be used for all devices. A better design generates a private signing key for each customer, although customers who individually purchase protection may also have their certificates signed by the same private key. And there's also this concept in a lot of cloud architectures of bring your own certificate. So bring your own certificate and use it instead of using something that's managed by some provider. The private key used to sign the device certificate must be stored in an HSM or equivalent. The network must be configured such that the HSM will only accept cryptographic operations from the enrollment and management service. All data, commands, reputation policies, configurations, and so on, and all binaries downloaded to the device must be hashed and signed. The device software will validate the signature and hash before any further processing. That brings us to Chapter 10's summary. One of the big challenges with cloud-based reputation checks is performance. Users don't typically want to wait a few seconds while the reputation of potential URLs is checked. Most of us have come to expect that websites are at immediate tips of our fingers and access and loading content should take place rapidly without delay. This presents tricky security problems. As we have seen, security decisions must be based on the objectives that are to be fulfilled by the security. And with that, we reach the end of Chapter 10. We will continue our conversations next week. Stay safe. If you have any questions, feel free to reach out.